Alright, so, does everyone have a guided notes paper?
Yes.
What? No, I didn't.
Alright, could you please put the markers away there? Thank you. Okay, so, our lesson today is on Newton's 3 laws of motion. Thank you for the extras. Okay. And we will begin with Isaac Newton. Isaac Newton was a philosopher that lived in England in the late 17th century, which is what?
1690.
1600s. Okay, the late 1600s, yes. I don't know if it was the 1690s. I think he was born in 1662. But in the late 1600s, and he is credited with developing 3 laws of motion. He is also credited with having said, "If I have seen further than others, it is only because I have stood on the shoulders of giants." What do you think that means? Everyone thinks of Isaac Newton as like a really important figure in modern science. He developed many things, including calculus. Why do you think that he would? What do you think that quote means? Think about it for 1 second. We can write it later, but Zoe, what do you think it means?
Does it mean like he's no greater than anyone else, I guess?
Okay, so he's showing
That he's being humble.
he's showing humility, right?
Yeah.
Very good. Sounds like he's a humble person. Helena?
Because he stands on the shoulders of giants, like being his friend, he has helped to see above.
Right. Anybody else? It's kind of like he's acknowledging that the people who, if they hadn't made the discoveries that they made before him, he would not have been able to get to the point where he was. You know, you can only get farther by acknowledging those who have come before you. Yes, Francesca.
I was gonna say like it wasn't all he's like recognizing the people and saying that he couldn't have done it alone.
Right. Exactly. So this he was kind of like at the Academy Awards, and you thank all the people that are helping you. All right. You'd like to thank the Academy? All right. I'd like to thank Miss Giovanni for taping this. Okay. So she's taping. Yes. Say hi to Miss Marta. Remember she came and visited?
Hi.
All right. Newton's first law. It sounds like it's obvious when you think about it. It's that an object that is at rest, like all of us right now, is going to stay at rest. And an object in motion is going to stay
in motion
at a constant speed unless a force acts on it.
Oh, that's flippy.
It has, what do you mean? This is the first law of motion. It has another name, but the real name of it is Newton's first law of motion. All right? An object at rest will stay at rest, but an object in motion will continue in motion unless a force acts on it. Yes, Francesca?
That's not always so. They have the little book and it turns it and it says an object in motion so will stay in motion. No, it says a body in motion. Oh yeah.
Same thing. I think that's probably how Newton would have said it more closely, a body in motion, because any object in the universe is a body. Okay? Have you ever noticed that when you're in a car and you're wearing your seatbelt, right? And your mom is driving, and she doesn't notice maybe, I don't know, there's a iguana about to cross the street. And all of a sudden, she notices this iguana about to cross the street, and she comes to a sudden stop. What happens to you? You go forward. Because your body wants to continue, right, you've been moving forward, so your body wants to continue moving forward. That's Newton's first law of motion right there. And that's called, what your body has, because it's been moving, is called inertia. Inertia is a property that an object has because of its mass. Because we have mass, we have inertia. The more mass you have, the more inertia you have.
Which goes with the
Which is why this law sometimes, since Zoe wanted another name for it, this law is sometimes called the law of inertia. Because your inertia is your resistance to changing in motion. Well, I'll leave it here. Do you think an object that has a greater, like, say we have a bowling ball and a tennis ball, which one do you think has more inertia? Kingston? Yes, why do you think so?
Because it's heavier, and I would think a tennis ball, if it was in a car, it wouldn't roll forward as much as a bowling ball.
Okay, and you could also think which one is easier to stop. If they were both moving at the same velocity, which one would be easier to stop? Your tennis ball, so it has less inertia. It's actually a property of mass, not of weight. Okay, we'll talk about the difference between mass and weight in a second. Are you hot?
Yeah.
It's right there. It's a property of an object that causes it to resist changes in motion. It doesn't want to change. The more mass an object has, the more its inertia, the greater its inertia. This was a question, but now it's a statement. The more mass an object has, the greater its inertia. Kind of like the relationship between girlfriends and chocolates. The more chocolates you buy them, the longer you'll keep.
I don't like chocolate.
I'm just thinking of food because it's almost lunchtime. All right, let's do. We should send you a basket. All right, guys. Love you. Second law. The second law establishes a relationship between force, mass, and acceleration. You already know what mass is, right? What's mass? What is mass? You guys know this. You all have mass. What is mass? Mason.
It's like how much you weigh in pounds, but it's not affected by gravity.
Okay, you have some of it. Good. Thank you for trying. Yes, Rachel?
The amount of space
That's volume, and you're so confused about that. Mass is the amount of matter in an object. So I'll remind you. Mass is, and like, let's see where we have it. Mass. Okay. Mass is constant. It doesn't change. Your mass on Earth is the same as your mass on the moon or Jupiter or the sun. Your mass is your mass, okay? It's how much matter there is inside of you. Your weight, on the other hand, like Mason was saying, your weight will change. Weight is a downward force that is caused by gravity. We'll talk more about that in a minute. Yes? The weight of gravity acting upon you. Yes, it is. So your weight will be different in different places depending on the force of gravity. Alright? So mass is constant, but weight changes. Alright? The law itself states that a force causes an object to accelerate, but its mass resists the acceleration. What's the law? Force causes an object to accelerate, but mass resists it. And a force is simply a push or a pull, something that has the ability to change your motion. That has to do with it, yes. Next we're going to talk about not everything goes in here. Okay? Not every little card has a question on your notes. Okay? Force is, I'm just telling you what a force is. Is that a force?
Yes.
I wasn't trying to be mean. Yes. The force is very strong with you, young Jedi. Force is a push or a pull that it has the ability to change something's motion. Okay, that's all. And so the relationship that he figured out was this little equation. Force equals mass times acceleration. Not your weight, your mass. Mass times acceleration. Force equals mass times acceleration. And force, like many quantities in our lives, has two different units. You know how we say that the standard or English unit of length is an inch, but the metric unit is a meter, right? Or a centimeter. Force has two different units as well. The unit for force in the standard, we call it standard or English, or the British system, Mason, is what? What do you guys? It's force, not mass. No? Nobody knows? Pounds, yes. So forces are measured in pounds in the English system, or the standard system. Alright? Forces are measured in newtons in the metric system. That is the unit that you're going to be working with a lot more in this chapter, because we like to use metric units in science. So you're going to be using the newtons. And just to give you an idea, a newton is a little bit less than, well, a newton is less than a pound. It takes 4.48 newtons to make 1 pound. There's your conversion.
Ready, set, go.
And the way that we get the units for, or the way that we figure out what a newton comes from, is from the units in this equation. What's the metric unit for mass? Not weight, mass. Amount of matter in an object. Kilograms, right? So, if we have a mass of 1 kilogram, do you guys remember what's the unit for acceleration? Not velocity. Do you remember velocity?
Wait,
Nico?
V2 minus V1 over...
That's an equation. I'm looking for a unit. What unit do we measure speed in?
Oh, kilometers.
You
Miles.
measure speed in
Miles.
kilometers?
Or miles.
You measure speed in miles.
Oh, no distance.
I'm asking for speed.
Miles per hour.
Okay, give me another one. Give me,
Kilometers
think
per
in
hour.
metric. Okay, think smaller.
Meters per hour.
Meters
Per
per
second.
centimeter.
Meters per second. Remember seeing meters per
Inches
second?
per second.
Meters per second. Meters per second is fine, thank you. So meters per second, when you accelerate, you go a certain number of meters per second. Meters per second squared is acceleration. So a kilogram times 1 meter per second squared is a newton. That's where that comes from. Sure. Can anyone think of an example of the second law? Like, how can you show that force equals mass times acceleration?
This is the actual.
Mm-hmm. Yes, Lena?
If mass was just against force,
Mm-hmm.
it would, and acceleration is what force makes you do, the object do.
So how about a comparison? Think about this. If I exert the same force on 2 masses, okay, like I have, let's go back to our bowling ball and our tennis ball. If I exert the same force on the 2 masses, will they accelerate at the same rate?
No, because the bowling ball is heavier.
It has a bigger, let's be scientific, it has a bigger mass. Alright? Because it has a bigger mass, it will not accelerate at the same rate. Okay? So, this brings us to our third law, which is everyone's favorite to recite. Every action has an equal and opposite reaction. Can anyone think of an example of that in real life? Rachel?
Newton balls.
I think those are called perpetual motion balls, but, can anyone think of any other example?
Like you're playing like baseball
Guys.
and you hit it.
If you're playing baseball and you hit it, but don't I hit it in the same direction that it flies? But the force that I exerted with the bat is going to end up causing the ball to move in the same direction that I was swinging the bat. Right, that's not an opposite reaction. How about a skateboard? What do you?
When you push it to the one side, it turns on the other side.
You push your foot back and it makes you go.
Push it forward.
Swimming is a very good example. You push back, you push your hands back against the water, and it makes you go forward. Okay? Yes, Nico?
What if you were in space and you saw like this rock? Would you push it? Would you go back in the rock? Like,
Yes,
fly apart?
exactly. You would fly apart. Just think about, you don't need to be in space, Nico. If you're in the water, like if you're in like a little rowboat, and you push something, when you push like a float, like if you're on a floaty and there's another floaty, right, and you push against the other floaty, what happens to you?
You get pushed
You
back.
go pushed back. Okay, that's a perfect example of the third law of motion. Okay, this law deals with pairs of forces because all forces act in pairs. Whenever one force, like I'm exerting this force on Rachel, Rachel's body is actually exerting a force in the opposite direction on me in the same amount. All right. If there's this Kleenex on the table, right? This Kleenex is exerting a force down on the table, but the table is exerting a force back up on it. Now you say, now how do you know that the table is exerting an upward force, Miss MJ? Because if this table weren't sturdy enough, the table would fall. That's how you know it's exerting a force. And another thing to consider is your muscles exert forces, right? You know that your muscles all come in pairs?
Yes.
Because, you know, you have your biceps, right? Your biceps does, but your heart has 4 chambers, and they have to do opposite things. So your bicep exerts forces going this way, but your tricep is doing the opposite at the same time. That's why your muscles exist in.
Your 2 tongues.
Yeah, I was gonna say, where's your other tongue?
It's not an other tongue. Your tongue is made up of muscles
Yeah.
inside of it. Like, okay, it's not this arm versus this arm. This arm has muscles on both sides of it. Make sense?
It's like a right and a left.
Your right tongue and your left tongue.
Okay.
Alright, so,
Like when people get that thing done, like how
Yeah.
split in.
You actually have to do it.
okay, the net force, guys, net force is the total of all the forces that are acting on an object. Because at one point, I may be pushing this way on Rachel, but Mason may be pushing that in the other direction on Rachel. And what if our force is exactly the same?
I'm not going anywhere.
You're not going anywhere, and that's called equilibrium. Equilibrium is when the net forces are 0. So net force is the total, and when the total is 0, you are in equilibrium. Sounds like the word equal, right? And this brings us to one more concept called momentum. Momentum is, go for it. I saw you.
Like, because like in softball, like I was talking about it yesterday.
Uh-huh.
Like if like you have the ball and then
like the first base and the first base, you kind of move to the base to get your momentum. To kind of like help shoot.
Okay. And did you know that in the like in a group of objects that are with each other, the momentum is always going to be conserved. Perfect example of this would be if I had two like tennis balls, or have you ever played pool?
Yeah.
Yeah.
Okay. You know, you take your cue stick and you hit the 8 ball, right? And then you try. I tried to. So I hit it into this whole triangle, right, of balls, right? What happens to the 8 ball? It doesn't go. It either bounces off, but eventually, a lot of times the 8 ball will hit the other balls, and the 8 ball will stop moving, right? But the other balls will start moving. So the momentum is conserved in a system. It means that the total momentum, even though one ball lost its momentum, the momentum just didn't disappear into thin air. It got transferred. That's called the law of conservation of momentum. Which is momentum can be transferred, but the total momentum stays the same. Momentum is a measure of your mass times your velocity. So what do you think has a bigger, according to that definition, mass times velocity, what do you think has a bigger momentum? A freight train or a caterpillar traveling at the same velocity? Freight train. What about if you have two caterpillars, they're having a race, and one is going faster. So they have the same mass, but one is going faster. Which one's going to have the bigger momentum?
Faster.
The one going faster. You understand the two things that are acting upon momentum? Mass and velocity. Momentum is measured in kilograms times meters per second.
Well, you have to take into consideration they have to be born on the same day to have the same mass.
They don't necessarily. What if one eats more than the other?
But don't they all eat at a constant rate?
Who said?
I said that's what.
Do babies eat at constant rate?
No, I
No,
didn't
they don't.
I'm kidding. Yes, sometimes.
Okay, we have two related concepts that go with, one goes with the second law,
Wait, so like
and one goes with the
momentum-
third law.
Momentum, when you do like when you have the thing, the pool ball or
Uh-huh.
something,
Billiard
is it
ball.
sort of like Newton balls.
Yeah.
Okay.
Yes, very much like it.
Sure,
Sure, we can.
You're getting me some.
I know.